it going?
Hey, what up?
I can see the excitement in your eyes.
I haven't really done anything, so.
I mean, same day last week. Just updated images, that's about it.
I'm half hoping it doesn't get to my thing.
Oh, there will be. I'm pretty sure our posters, each presentation should be 1 to 10 minutes.
Probably not, but
If anything, it'll be safe for Friday.
I know.
So,
I'm sure.
I'll just try to hack into something.
Not that energetic.
meeting.
It's got witnesses.
Distribute. This is probably for the group and we start for next class. So how are you going to print it? Do you remember procedures from last time we went through it for Boston?
Get the card from you.
Huh? Yes, and there should be an email of this person from agricultural printing for fabric, right? Because if it is fabric, you can jam it and put it in a pocket rather than rolling. So we want to distribute or arrange cards. And after all pages are ended, the last 7 pages are copies of the last version of London poster, which were printed at the last minute. I'll announce once again. Everything is good. Okay, let's give chance to Daniel to be first. Right? You're still teaching at 5.
Yes. That would be the change.
And please make notes if you need.
So
So it will be not recorded again today. So if you want to memorize something, just write down.
So what I changed though from last week was I changed the color scheme from a couple of the atoms because I think whenever I showed it on previous examples, the bromine, cesium, and carbon, they were all pretty much like around the same color, so it's kind of hard to distinguish different atoms. So I tried doing that, but these models, I'm gonna change them later. I guess I forgot to look at them. I was busy playing with other stuff. I changed around the introduction and computational details. So top right, I got rid of those tables with the relaxations of the electrons in the holes. Instead, I guess I'm gonna leave that bigger corner of the section to the orbitals. But I gotta relearn how to do the orbitals, so that's probably why I haven't seen an updated version of it. But one thing I did make kind of a bigger improvement. I would like some feedback. I don't know if this is also better. Well, trying to show the difference between the two models right here with using the black line. I used and one more of my updated versions. The ligands actually have bonds to them. For this version I gave it to Dimitri. I forgot to put the bonds on the ligands, so yeah. So just pretend there's bonds there, just not on this version at the moment. But so that's probably why you can see more clearly, I guess, the difference with the cesiums and the leads on the surface of the ligands. Instead of trying to use the whole model, I just take a little zoomed in version of that version right there. So density, states, absorption, I didn't really mess around too much. And photoluminescence, I left that section there blank because I had a hard time trying to get a file called for master optics. So that's something I'm pretty much gonna invest a lot of time from today till Friday to try to get the.
Not Friday, it's Thursday. Thursday evening, you need to submit everyone. Better if we all submit for printing by Wednesday evening. Thursday evening is like very late deadline. They will not print on.
They don't print on Fridays?
Well, you can print on your own expenses at FedEx Kinko, but university will not do.
Oh, okay. University won't pay. All right. So I guess I'll pretty much work on it all day tomorrow then. Well, tonight, I guess tonight I'm gonna try to relearn the homos and lumos, or trying to get better pictures on that. Pretty much with the same color scheme as I have up there.
Did you got help from suggestion from Aaron about how to generate for Master Optics?
Yeah, he.
Were you able to log into NERSC and run this code?
Oh yeah. I could log into NERSC and download a lot of stuff. I just
No, not download. Run.
run. Well, I mean, I know how to log into NERSC, so if I can log into NERSC, I just had a hard time trying to run the file. But yeah, I could log into NERSC. I just can't. I just have something.
to ask for.
Yeah, I was planning on doing that.
What have you done to equations? Last time it was.
I had feedback from people telling me to get rid of them, so that's exactly what I did.
Who?
There was about 3 or 4 of them had.
No, who? Names. Who told you to remove equations?
When people write feedback, they usually don't leave their name on the paper, so I don't know. Reading.
No, probably the comments were be able to explain every equation.
Oh, okay.
Immediately learn how to explain equations, not remove them. Put them back.
Put them back. Okay. Yeah, it's not a problem.
Yeah, the crowd of Sanibel is definitely going to want to look at your equations. That's going to be like the top thing.
That'll be the fun part for me then. But yeah, like
You end in a theoretical group.
Mhm.
You expect to do direct equations every day, right?
I'm expecting. Okay.
Sure.
That's funny too. This bag says "sure" too on it, so that's kind of funny. But yeah, so you said posters by Thursday evening, right? With the same with the same person in the agricultural department. Okay,
Yes.
yeah, it's not a problem. I'll get it all done. Not a problem. But yeah, I'll take any feedback.
Can you summarize again? I'm sorry to ask silly questions, but what is the goal? What is not known? What is the new knowledge that you are targeting first, and then what are your conclusions?
What is the goal?
Yeah.
The goal.
You're trying to present to dry run your presentation, not to report changes.
To dry run. Well, I just figured I really couldn't. So the goal of my research is to try to, I guess, try to find out the differences between the photoluminescent yield between 2 different surfaces, surface interactions. One model being a cesium-rich, which is depicted all the way in the middle, top left, A file. And then the second model I'm comparing that to is a lead-rich system, or a lead-rich interaction between the same ligands, same ratio, same model. Everything's the same. The only thing different between both of them is the surface, is the interaction at the surface. So one thing that's a negative thing that in this field of research that people most likely want to avoid are trap states, because the charge whenever you excite this material will get stuck in this trap state, and that charge will forever be lost. So because of that losing that charge, we get what's the word called? It's not efficient. It's negative. It's the opposite of what we want. So the goal is to try to minimize these trap states as much as possible. And some of my earlier works, I guess I haven't shown it yet because I still need to rework my orbital section. But there seems to be a trap state on the HOMO orbital of the cesium rich surface. So that could pretty much be a Debbie Downer for this type of application due to that trap state, since most of the molecules, whenever you excite something from that'll get excited into the unoccupied orbitals, whenever it lags down to the occupied orbiter, which is the HOMO in this case.
Do you enter? So, which material do you study?
Perovskite,
More specifically,
cesium, lead,
bromine.
bromide. Yeah.
Okay. Do you have only cesium, lead, and bromine in your model?
As part of the perovskite structure, yes.
No, in the complete model.
No.
What else do you have?
Charged ammonium and acetate ions as
What's
the
the common
ligands.
name for them?
Huh?
What is their name? Why they needed?
Why are they needed?
Don't you want to call them ligands?
Yeah.
Okay, so why ligands are needed?
To passivate the cesium, the lead atoms that are on the surface,
To remove trap states.
to remove trap states. Okay.
And why do you compare cesium-rich and lead-rich?
Why?
Yes.
Because that's what the material is made out of. So
No. What are expectations? Why do you decide to compare them?
why did I decide to compare them? Because the morphology is different from both of them.
But which one so you do not have photoluminescent spectra yet, but which one is expected to be more optically active?
The lead-rich system.
Why?
Fewer trap states and the rate field temperature is kind of a little good.
Did you know it intuitively before you started the calculations?
Did I know that? No, I was naive in what would happen.
But if you wouldn't be naive, but you do not have calculations.
Would I come up conclusion? Honestly, I'd probably say the cesium-rich system, but not really because isn't like cesium like really bad in water? So,
Huh?
well, I kind of root on the lead-rich system because I know that like if you drop pure cesium block into water, it's kind of bad, and perovskites are.
But it's not a matter. It's
moisture?
already oxidized. It will not. And cesium, same as sodium. If you drop it in water, something happens. But if you have sodium chloride, nothing happens. So this argument, no.
Or it doesn't work. All right, yeah, it's only when it's pure.
And atomistically.
Atomistically, what would I say is better?
Yes. So when you have lead terminated surface, it has inhomogeneity, although it is compensated by ligands. Who knows where these ligands will or will not make this work? So it is maybe not efficient. And if it is cesium-rich, then cesium already works as in some sense, a ligand and protects previous layer of lead. So the cesium, intuitively, without any calculations, cesium is expected to be more optically active. But you may formulate your calculation as a hypothesis to prove whether cesium is terminated surface is better, prove it right or wrong. Okay, what is your conclusion based on your calculations that you have?
What is my conclusions? That the lead-rich system seems to be a better candidate for.
Based on calculations, do you have arguments for this? There are two different things: your scientific intuition and calculations.
Yeah.
If they coincide, it's great. But,
They coincide. Okay. What do you mean by calculations, though? I thought these were all calculations.
based on your chemical and scientific intuition, you can predict outcome of experiment and calculation without doing it, just based on your experience with similar systems. And therefore, you pose a hypothesis, what should be the answer. Then you perform calculations and tell whether my original hypothesis was proved wrong or right.
Okay.
So just try to repeat what are your conclusions?
What are my conclusions?
You know what? When you will be traveling, you need, when poster will be ready, you need to write down a speech, not with jokes and informal things, but going figure by figure what you want to tell about it. It will be serious. You need to be very specific and quick in explaining technical details.
Explaining technical.
Make dry run, same as you do for your, like, in the future thesis defense or practice.
Yeah.
And now conclusions.
Um. So when I predict that the leverage system does have the better candidate for these photoluminescent properties due to the fact that when I looked at the dynamics such as the red field tensor, you could see the higher amounts of coupling that's found in the cesium-rich surface compared to the lead-rich surface because of well, one piece of indirect evidence is this, due to the fact that the coupling is here, it takes longer to relax, and the fact that it might take a little bit longer to relax than the lead-rich system does indicate that there are probably a higher number of trap states that are found in the cesium system than it is in the lead system. That's my conclusion right there. I'm not sure if you wanted more out of that.
Okay, let's thank Daniel. Any questions or suggestions? What can be improved in the remaining short time?
Are you planning on putting in like a figure to replace your table on?
No, I think I scrapped that.
Yeah, you removed the table and you didn't put anything instead.
I was gonna put the orbitals instead.
Okay, but were you planning to convert the old table into graph?
I don't know how to.
Come on. You know how to use Excel, right?
Sure.
So convert column of data into a figure. It's not a big task, it's like for undergraduate or high school. Please try. More questions? Please make some suggestions or just wishes to do the poster, and let's thank Daniel once again. Whew. Aaron, would you like to, or maybe let's give a chance to Wendler, because he probably needs the comments. And you'll be able to navigate, right?
Yeah, yeah. All right, so I guess generally speaking, what I'm researching is the charge transfer dynamics at perovskite and charge transport material interfaces in a perovskite solar cell architecture. So I'm kind of doing I'm showing two different projects, or I guess I don't know what the appropriate word would be. So this middle column is my old project that I've talked about a bunch of times. And what I'm trying to do is put my new stuff into this right column here. Let's see. So the way that we're calculating on all of this is we're taking these atomistic, I suppose you can't see what I'm pointing at on there. We're taking these atomistic models and optimizing them in VASP using DFT in the PBA, functional PBE. And so once we get those optimized, I guess you got the PDOS plots here, we can start to look at the band structure. And you can see that I suppose I should mention the difference between the models, that would make sense. So the difference between these models is just the ligands that are adsorbed onto the titanium dioxide nanocluster, and I guess the orientation of the nanocluster. So if you take this one and just rotate it up and replace these hydroxyl ligands with acetate ligands, with isopropoxide ligands, then you have this model. Yeah, so we're looking at the difference that introduces to this system. So I guess if you look at the projected density of the states, or actually try to plot out the orbitals, you can see that the
Can you make a little break?
Yeah.
For 2 minutes?
Absolutely.
Then you'll get tea.
Oh, are you trying to get it recording?
Yeah.
Did you start in class or video conference?
Video
Do you
conference,
remember?
video conference.
Okay, so that should be correct then. Oh, it's not in the call. I wonder why not. That would be why it's probably a blue screen. Interesting. Systems turned on. Let me try to make it. Mind if you see the computer real quick? I don't see the number from the call. Five, 666.
You are the only participant in the conference.
Reset the camera.
You are the only participant in the conference.
there we go. Yeah.
Okay.
Camera just lost connection for some reason. Sorry.
Thanks so much.
Yeah, you're welcome.
No multimedia room.
Okay, that would just be. Yeah, I don't know why it keeps. Check. And then, yeah, we'll need to use this one for the audio. Okay, that should be it. Sorry about that.
Thanks so much for
Yeah, you're welcome. Here, this is yours.
Okay, so we're good to go?
Yeah.
Okay. So once we run density or DFT and get the ground state electronic configuration, I guess the first thing that you can do is take a look at the band structure, and in the hydroxyl case, you'll notice that the upper edge of the valence band is in the, the upper edge of the valence band is localized on the perovskite, and the lower edge of the conduction band is localized on the titanium dioxide, which is preferable for a solar cell application because that will lead to a charge transfer once the photoexcited charges relax to the frontier orbitals. In the acetate model, however, you end up with both of the band edges being localized on the titanium dioxide. And so if you do get a charge transfer, it's likely to be very short-lived, not preferable for extracting those charges, because both of the photoexcited charges are likely to land in the titanium dioxide, just exciting that one species energetically. And so once we have the ground state electronic configurations, we can calculate the transition dipoles and the oscillator strengths in order to figure out the absorption spectra. And so there's a pretty negligible difference between the two of these. In the acetate model, the absorption gets shifted slightly upward generally, and I mean the D peak kind of gets squished a little bit, and the B peak seems to get perked up a little bit, but there's no significant difference, which suggests that the perovskite is essentially responsible for all of the light absorption, for the most part, anyway. Okay, so once we have all of that ground state, I guess the ground state observables figured out, we move on to molecular dynamics. So I heated the system to 300 degrees Kelvin over, oh God, it's on here somewhere. Yeah, over the course of 300 femtoseconds at half femtosecond time steps. And then molecular dynamics was run for a picosecond with 1 femtosecond time steps. And so from that, we can calculate the couplings between orbitals, between adjacent time steps, and use that information to calculate a Redfield tensor. And small portions near the frontier orbitals are shown here. You can see that essentially what these represent is basically transition rates, I guess, from this orbital to this orbital. So you can see that it essentially only really allows for transitions between neighboring states in both systems. I mean, there's, a slim chance that you could go some other route, but that's not, I guess, the likely path that it will take. And so these plots show the actual orbital occupations as a function of time. So each slice of this represents the occupation of one orbital, where the height is the occupation of it. And then time is represented on this axis kind of going off to the right here. Yeah, I guess that kind of supports what I was just talking about with the Redfield tensors. And then we can also make these graphs down here, which I need to make the fonts a little bit bigger on because that's impossible to read. But so I guess in these graphs, the green background color represents no change from the ground state charge distribution. The darker blue and purple color represents a positive charge localization, so that'd be a high hole density. The brighter yellow and orange represents a high electron density. So these top graphs both show the energetic distribution of charge as a function of time. The time axis is logarithmic, by the way. And then these bottom ones represent the spatial distribution of charge in the z-axis. So these two models are shown here so that you kind of can compare, you know, where this is on the actual atomistic model. So, I mean, at the end here, you can see that you've got a high hole density localized right at this top layer of the perovskite and a high electron density on this bottom set of titanium, of the titanium dioxide. So this actually is a charge transfer state in this case, whereas in the acetate model, you kind of have a very scattered charge distribution here. You get a slight backwards charge transition from what we're looking for in this device, and then both excited charges end up on the titanium dioxide as the system relaxes. And these are both chosen to be the transitions that have the highest oscillator strength for both of these. And I guess so I looked at, you know, the top 20 oscillator strengths for each of these systems and calculated out the relaxation times for each of those. And on these figures, you can kind of see where that is by when the electron and the hole density sort of, it stops changing, I guess. You know, it ends up landing somewhere and then stays there. So at that point, it's done relaxing, so there's your relaxation time. And I don't have enough room to try to squeeze all this stuff, so I have this over here for now. And so this is my plot of relaxation times for these systems as a function of dissipation energy. And what I mean by dissipation energy is in the case of electrons, it would be the energy difference between the photoexcited state and the LUMO. And in the case of holes, it would be the energy difference between the HOMO and the photoexcited state of the hole, I guess. The state that the electron left upon photoexcitation. And so you can kind of see that, you know, there's local energy gap. It obeys the energy gap law in local segments, but it doesn't appear to obey the energy gap law globally. At least in most cases, I guess the acetate holes seem to, and the holes kind of seem to obey the energy gap law. I guess the electrons don't really. I guess I don't really know why that would be. I'm still not really totally sure.
Ask your group.
I don't know if anybody has any insight as to like the conclusion I can draw from that.
In written form or privately later.
Yeah.
It may deal with different density of states, sparse or dense, and if absolute value of density of states is different, and also how the density of states changes as we go further off from the gap. So if the gap law is designed for sparse states, but if it is denser, there are chances to jump through the neighbor, and instead of slowing down, it could be acceleration.
Maybe scroll up on your feet, visualize it. Like the holes there. depends where density stays.
Yeah.
So that could be one reason.
Okay, yeah, I guess
Figure
there's
a little better.
just more likely to be kind of a straight shot down as opposed to kind of having to skip over. By the way, if anybody has any suggestions on like what I should try to cut out of this middle section, including, you know, this plot down here, because I would like to try to get, you know, whatever I'm going to do for my last project onto here if possible, and then, you know, the new project over in this side. But obviously I don't quite have room for that, so something has to go. I don't know, whatever seems the least relevant, I guess, just let me know. So then for the new project, I generated a whole bunch of coupling stuff for, you know, doing the whole Redfield analysis again. Unfortunately, the trick that I did to make it work made my data useless, so I gotta redo that now. But I guess this is the atomistic model that I'm looking at manipulating with an electric field. So you have cesium, lead, bromide, perovskite, the same as in this case. And then you have the titanium dioxide from the hydroxyl model over there. It's all the same model. The difference is that we now have a whole transport material, namely spiro-omitad. And so what we're trying to do in this case is figure out how the excitonic behavior responds to an electric field. And so...
Be careful with the word excitonic. If you're not sure, tell excited state.
Okay, yeah. Well, because I know an exciton is like...
It's a quasi-particle when
yeah.
electron hole are bound and move together.
Yeah.
So, it is exactly the audience who will pick you on the inconsistencies.
Yeah. So, I took 100 states above the HOMO, or sorry, below the HOMO and 100 states above the LUMO, and integrated out 2 dimensions so that only, you know, this dimension is left, and plotted their densities in here. So each of these slices represents an orbital, and the this axis here represents, you know, distance in that model in angstroms. And so you can kind of see where each band is localized as far as what species is on here. Yeah, just a nice visualization, I guess. I don't know if I should really say too much about that or not. I don't know. And so in the ground state, what we're doing is approximating, well, I guess maybe it's better to say we're calculating how the ground state we're figuring out how the energetic distribution of the ground state orbitals responds to the electric field. And the way that we are calculating that is by using a first order dipole approximation.
Which you may navigate us right now.
What's that?
Show which equation illustrates your words and the figure.
Oh, look, that's right across. That would be these equations here. So this one in particular is what we're really looking at. And so the nuclei represent the positive end of the dipole, and since that's constant for every orbital, that never changes, you can essentially just remove that from the equation and you still get the same relative structure that you would have otherwise. We use this equation with the only real difference being this vector is just replaced with a scalar since it's pointing, you know, straight up or straight down, and this r vector is replaced with the z position.
We keep scalar product, but we intentionally orient the electric field along z axis so that vector
Right.
consistent on z projection.
Yeah. So you just end up with the magnitude of this times your z position of your orbital.
So z projection of field times z projection of dipole.
Yes.
How this equation corresponds to the previous one? Is it the only correction, or it is lowest order in perturbation theory?
It is the lowest order in perturbation theory.
Why wave function is not changed? Why you assume that wave function is not changed by this perturbation?
Because that would make calculations much more difficult, I guess.
No.
I don't know.
Ask Aaron. He was getting credit in the advanced CHEM on the subject, and he may give you the answer if you can ask him.
I think it's just a scalar correction.
In the first order perturbation theory, wave function didn't get any change. It's only energy that is being corrected to the first power of the interaction matrix. And if, in order to get corrections to both energy and wave function, we need to move to the second order correction, which is like negligible compared to first order if the interaction is small. So it is not free volus decision because it is easier. It is literally dictated by rigorous perturbation theory that if you are in the first order, there is no change to wave functions.
Mhm. Okay. Should I change the wording here then, do you think? Because I mean, I guess that would technically still be kind of accurate. I mean,
You can just remove eigenenergies of Kohn-Sham Hamiltonian
oh, okay, yeah.
or energies of orbitals. You'll hear some suggestions from audience. Yeah, not quite correct.
Okay.
First
So,
order, oh, sorry, that's that. So first order correction don't mix states.
Correct.
yes.
I guess I'll just look at back to view. So I remember there was one where it was
There is time-independent perturbation theory. First order is really easy.
Yeah.
Matrix element of interaction Hamiltonian gives correction to the energies. That's it.
okay, yeah, I guess. Now that I made this far.
Okay. So, by using that approximation from first order perturbation theory, we can calculate out, the energetic redistribution of the ground state orbitals. And that looks like this. And so what we did was we calculated out the what magnitude of electric field you would need in order to make the HOMO actually meet the LUMO in energy. So that's what you can see here with this horizontal line. And so as a first order approximation, what I'm trying to do right now for molecular dynamics is I'm taking the molecular dynamics trajectory without an electric field, and then I'm computing the couplings between adjacent time steps without an electric field, and then with these two values of an electric field, because I guess the electric field is not likely to have a drastic impact on the actual trajectory itself. I mean, it shouldn't change anything in significant enough of a way, I guess, to alter how strongly the electronic states are coupled, because you still just kind of have nuclei moving around, I guess. I don't know. And so once I get that data, then I will...
London?
Yeah.
I missed the pencil, I will not write, but you verbalize it. The model has both positive nuclei and negative electrons.
Yes.
But net total charge of a model is 0.
Mhm.
So the center of mass of a model will not move
Okay.
due to electric field. Therefore, we can approximate that we can neglect influence of electric field on the trajectories.
Okay.
But for larger wavelength electric field, of course, there will be some change in trajectory.
I guess I don't know how large this electric field actually is. I can't really visualize EVs per angstrom. Vast
But you
giving me
have
warnings.
is already strong enough.
Yeah.
There is no guarantee that we are in the small field regime. You mean add notations or like arrows telling where is the valence and conduction band on this diagram, just to help reader. Okay.
Yeah. Yeah, I guess the best way to do that would be off the top of my head. Yeah, so I guess I'm going to. I thought you sent me a script that like rewrites the energy pop file. I don't know. I couldn't find it earlier today. I was looking for it.
I can resend it.
Okay, yeah, because I was just gonna write up a new one here. Like I rewrote the script that did this. There was like a very small logical error in it. So I don't know. But yeah, it shouldn't be too bad. I don't know. Whatever. So yeah, I'm gonna calculate the new density of states and the new absorption spectra. You know, assuming these orbital energies. And so I'll have, I guess, you know, like 3 of those to kind of compare with each other. And so if anybody has any suggestions on how best to try to use this space to do that, I'm all ears. Because if I expand this out, then this is just going to take up the whole freaking column. But I don't know what I would be able to kind of sneak in along the side of here, if anything. Yeah, I don't know. Because I'm also going to have this sort of stuff that I'm probably going to try to, you know, put up next to each other.
Gradient, it will take probably all the space.
Yeah.
And if it is too late and you do not have time for any changes, and you are not comfortable with white space, mark white rectangle and write comments and emails if you need preprint of this work.
Yeah. That's my poster.
Okay, but then, Glendon, any questions or suggestions? If no, please collect written feedback, if any, and we need to go across 3 posters at least in the remaining hour. And now, for sure, no.
I just closed mine out now.
You put the one by Fatima, and let's put the one by...
I guess for time, I'll just skip past most of the introduction stuff that I would normally do, but I guess I'll say basically that we're looking for polaron formation and lead halide perovskites, which have been known to, or it seems like an intrinsic feature of these materials in the excited state that they form polarons for both positive and negative charges. And for my title, I try to make a play on words. When life gives you lemon, make lemonade. So usually people avoid polaron formation because it's not good for photovoltaics or charge migration, but if life gives you localized charge carriers, try to make light. I don't know if people get that at first, but yeah, so we're going to try to take these polarons and make them emissive in the IR region because some experiments have shown that polaron absorption happens in the IR region where people would be interested in getting an efficient IR emission. And just to illustrate polaron formation in these materials, so this is a 2D projection of our perovskite cluster, our nanoparticle, surrounded by passivation ligands. And this black line represents an isosurface of adding an additional electron or negative charge into our cluster, and then these arrows represent the migration of cesium atoms inside the perovskite structure, which, because they have positive charges and they're going to reorient around due to the negative charge that's introduced. And that's what happens in space. And then for the polaron formation, polarons have bound states. And in the spirit of Walter Cohn, you can approximate those bound states as like averaged of the electron interacting with the average ionic charge that's moved around it. So it's kind of like the Coulomb interaction. You kind of see the energy spacings will ideally follow the same type of trend. We have our electron at the lowest bound state, and then the bound states take on hydrogenic wave character. And so we have our model, we have an idea of how polaron formation forms, and what we try to do is we try to calculate photoluminescence quantum yield. So we calculate radiative recombination rates using Einstein coefficients from our spinor cone-CHEM orbitals. And we use red field theory to determine non-radiative relaxation in these materials. And so the methods, so traditionally when people were first working on these problems, there's a man named Froelich who attempted to try to solve this problem. So, and the Hamiltonian he came up with was kind of the standard Hamiltonian. So you have the electron degrees of freedom, your independent phonon degrees of freedom, and then polaron formation is the coupling between electrons and phonons. So you have a cross term in there, and then these is just the convenient second quantization ways to represent these. So you have your electronic energies, your phonon energies from your creation and annihilation operators, and then you have the off-diagonal elements which couple electronic and nuclear degrees of freedom. And they have a bunch of, I guess I'm just going to have to work on describing the couplings and then the parameters in them a little bit better. But we don't have to go too in depth to them because we're going to approximate them using cone-CHEM DFT. So we assume that our electronic and nuclear energies, we can just use the adiabatic states for the ground state, or for our ground state method. And then to approximate the polaron formation, we add an additional charge and let the model optimize around that charge. And that's represented by this plus delta R. So a little bit of nuclear change around it. And then the rest further theory that I'll get into right now is how we calculate our excited state dynamics. So we calculate non-adiabatic couplings on the fly. Using spinor cone-CHEM orbitals. So these spinors are made up of two components, spin alpha and beta. So that's why we have two components here, two components here. And we compute those, and then we process those, which I'll describe later, to fit into our Liouville von Neumann equation. And then essentially it gets lumped into the dissipative part of our equation. So it describes dissipative transitions during a molecular trajectory. And so from here, I'll just describe some of the models or some of the calculations that we did and how we visualize, or how I'm going to attempt to explain them using these visuals. And so to calculate binding energies, we need a reference energy to our polaron formation energy. So to do that, we use a Frank-Condon approximation, which essentially is you either put in either just a single electron or introduce a single hole or both into the model, and then just do a single point calculation. So you don't let the ions move or optimize around the new charge. So that's kind of the definition of a Frank-Condon transition. And so we calculate those, and then we are looking at various different models, or different polaron formations first. So what we'd have to do is look at either a positive polaron or a negative polaron, or injecting just one charge into each of them. So here's a negative polaron, so we just put in an additional electron, and then let it optimize to form the polaron bound states here. For the negative polaron, same deal with the polaron, we remove a charge or add in an additional positive charge, and then let the system optimize. And then eventually we want to get to the point where we feel confident about these results and then model a photo-induced polaron. So you have positive and negative there. So you photo excite, and then eventually they dissipate to the band edges and then form a polaron. And then from there we'd be able to get optical transitions in the polaron regime, and then also transitions across the gap for the polaron. So model both of those at the same time. And then another model that we'll eventually try to get to, which I've been playing with, is looking at how nuclear reorganization affects the efficiency of IR emission for the polaron. So since the energy spacings are so small that small reorganization energies might actually have a big influence over the how well they emit, because from Marcus theory, there's an inverted region for how efficient your emission can be. So there's like an optimal point where you want your reorganization to be. If you're away from that, your emission is not going to be very good. So we're trying to incorporate that into our models as well, because the red field theory typically doesn't account for reorganization energy. And so this is the band picture, and this is what would be like the traditional Marcus picture. So this black line is our ground polaron state, and then this parabola is the excited polaron state. And this image is actually wrong. This state should be over here quite a bit. I have to play with the code to get the potential energies to line up well, but I'll have to do that. And then this line just represents the wave packets initialized on the excited state. And
It's not really clear on like printed versions.
on this one?
Yeah. This looks like there's a little bit more going on than what I can see.
There's not. Oh, you probably don't see the gray line very well. So it should only be 3. It won't let me zoom in anymore. But there's 2 parabolas, and then here it's just a Gaussian centered at the middle, and then I just zoomed in so you can't see the top of it. So it's just a cutoff Gaussian. And then these are the typical Marcus rate equations, where for our couplings we have non-adiabatic couplings, which we calculate, and then we can also for non-radiative transitions. And we also compute the reorganization energies, and we can play with temperature as a parameter to see how the rates are.
What is the rate of lambda divided by delta G? Which one is bigger? For the figure that you showed.
It's a good question off the top of my head. So delta G.
You can see it from the figure, if the figure corresponds to realistic situation.
Oh, this one, delta G, is much bigger than the reorganization.
Or smaller. So what's the definition? What delta G is much bigger than the reorganization energy. Yes.
Yes.
Yes. Negligible reorganization. Yes.
Right, for this picture. But this one should be shifted off a little bit more.
Yeah.
So in reality, so the picture is a little misleading.
Okay.
But yeah, I'll make sure to.
Because if they're really one under each other, then it is really all our approximations are really great.
Right.
To neglect any reorganization.
Mm-hmm. And so, like I said, these 2 last models are things we want to do in the futures. Or we don't have enough data to fully present on them yet. So for the rest of this talk, we'll be focusing on the negative and the positive polarons. And so the first set of results is focusing on just the brown polaron bound state. And so for both of them, I can show density of states for the valence band, because that's where the positive polaron is going to be. And black line represents the neutral or non-polaron model, just the regular ground state model. And you can see for all of the polaron models, I guess I didn't mention that we look at different multiplicities, or like spin states, so singlet, doublet, and triplet for all the polaron models. And that's what the colored lines represent. And the density states are basically all the same for the polaron models. And they show a slight shift, or like the band gap of across the gap widens a little bit for all the models. And so it's density states, and then using the Frank-Condon transitions, we calculated binding energies for all the polar models, and they range in like the 100 milli eV range. One of them's a little lower than expected, but the doublet and the triplet both show values that have been comparable to other results in the literature for whole polarons. So those seem pretty successful. And then we also compute IR spectra for the positive polaron.
Is it absorption or emission?
This is absorption. So ground state absorption, or polaron absorption. So IR spectra, so the units are in wave numbers, and the issue I had last time was I didn't change which column I was plotting. So this one should be right. So this would be the lowest energy transition.
Okay, so it will be like
It's like
0.05
Mm-hmm. Yep. For the single and the triplet anyway, they have about the same absorption on set peak.
And those are only electronic transitions, because in the real experiment they can be intermixed with
Surface vibration.
yeah, just vibrational transitions, which are also in this, especially
Yeah, like this, like 1200.
1500. Yes, yes.
Yeah.
For any organic, it will be strong peak.
Yeah, so these are just electronic state-to-state transitions in the potential law.
Okay. How would you justify that you are not showing vibrational contributions into the absorption spectrum?
I guess we don't have any. Well, I guess I would say you don't have
I
ND.
have a cheesy argument, which I'm not sure. Please correct me. It's just if we will asymptotically lower the temperature to absolute zero, the relative proportions of electronic contributions to infrared range and vibrational contributions will change ratio.
Mm-hmm.
The vibrational contributions will never get to zero, but since they differently react to change of the temperature, we will be able to extract all the electronic transitions.
Mm-hmm. I guess an experiment with it's time resolved. So you have like the ground state reference that has all the absorption. If you assume in the excited state, there's not many additional vibrational peaks.
Great. It's another idea. If it is femtosecond experiment, which is quicker than any period than any nuclear vibrations, then there will be no chance for quantized nuclear degrees of freedom to appear there.
Mm-hmm.
If it's like 10 femtoseconds or 50 femtoseconds, it will be all the electronic transitions.
Mm-hmm. I think the Aspire paper was on. I think it was on like 10 picoseconds because it takes at least a picosecond for the polaron to form.
Just
So.
keep thinking on the ground, you will get this question.
Mm-hmm. Would that be along the lines of what they're actually measuring polaron absorption?
Mm-hmm.
Okay. And I'll just mention the oscillator strength. So the color codes here correspond to the arrows in the spectrum figures, and they have, I guess the numbers don't mean much, but they're moderate compared to the negative polaron for the other model that we have.
And there is no reason to compare to neutral reference state because it doesn't absorb in this range. If you have no polaron intrinsic system, that it will start absorbing like at 50,000 inverse centimeters.
Then same deal with the negative polaron. So calculate conduction band density states. You can compare between the neutral ground state model, the polaron model, and we see another consistent shift which widens the band gap of all the states. And then there's not much difference between all the multiplicities for the states. And The binding energies for these did not come out as nicely as the whole model. There's a wide variance between them. So the singlet shows about 200 binding energy, so it's in the well. The doublet basically showed no binding energy, and the triplet had an unbinding, or it showed negative binding, which means that the condon transition had a lower energy than the.
So it was what Ben Jeffrey was showing, something like transitions with negative frequency.
Mm-hmm. Yeah, and comparing that to other results in the literature, they found for, I guess, a similar model for computation, their binding energies were on like electron volts consistently for their models, so like 1 eV. But the main difference they had, it was like an actual cluster. They didn't have ligands, so you could possibly argue that the ligands suppress some of the nuclear reorganization at the surface, but there's probably a little bit more at play, and there's probably a miscalculation somewhere too. So I just have to go back and double check those. Yeah, so then moving on to the IR spectra. And so for this model, compared to the positive polaron, its onset is at a higher energy, so about 1,000 wave numbers, which is like 0.2 eV. And all the multiplicities have it in about the same area at about 1,500 eV. And they all have, well, I guess they all have higher oscillator strengths than the positive polaron models for the lowest energy transition. So that would kind of indicate that if there was polaron emission or absorption, that the negative polaron would be more likely candidate, possibly, than the positive polaron. And so that's density of states and spectra for the model. And then now we'll move on to excited state dynamics. I just want to rotate my figure. Whereabouts me? So for right now, we only have results for the positive polaron excited state dynamics. I know I have some calculations going for the negative polaron, and there's, well, hopefully the collaborator has some calculations going as well too, so that we can have some results for the negative polaron within the next couple of months. But so we start by showing, or to, I guess, to do our dynamics, we have to couple electronic and nuclear degrees of freedom. So we do that using adiabatic molecular dynamics. And these figures show the energy fluctuations of the cone-sham orbitals along the trajectory. So these fluctuations correspond to coupling to phonon modes along the trajectory. And if you've taken enough statistical mechanics, you could probably have it burned into your mind that fluctuations lead to dissipation. So that's why we start with showing energy fluctuations of our models. And
Sounds impressive.
I'd assume people at this conference would. It's like they've probably been tortured with it enough, so they probably remember it. So you have fluctuations, and so to extract those fluctuations, or to extract the nuclear degrees of freedom that couple to electron degrees of freedom, we do some post-processing. So we do correlation functions, or autocorrelations of our non-adiabatic couplings, which is shown in the methods along the trajectory. And if you take the Fourier transform of those couplings, you extract out the phonon modes are coupled to those degrees of freedom. So you essentially get your spectral density, and using those rate equations, we can parameterize the Redfield equations, which describe dissipative transitions. So the plus or minus describe upward or downward transitions, and the indices correspond to 4 orbital components. But at the end of the day, pretty much all we're left with is those go away. And then the positives, they have a, they obey a Boltzmann distribution. So upward transitions are weighted by a factor of EKT. So they're pretty much negligible. So we're basically just looking at these two terms. And those are visualized as our Redfield tensors at the bottom here, which represents state-to-state transitions between orbitals. So our x and y axis are orbitals, and then the z components describe rates of transitions between the orbitals. And then I guess what I have to do next, I did some playing around. So basically just condense this, widen this out, move this up, and then put our green figures, our dynamic figures here to show. I guess I have to think about it, because I guess we could show like a green figure from, I don't know, since I'm doing positive, I can just show the whole relaxation. And then at the end of the dynamics, just put a bound state showing.
For Polaroid green figures, one may want to focus on much narrower range of energies.
Right.
If it is negative Polaroid, then just plus minus half eV or less in the vicinity of conduction band H. If it is positive, then about 0.5 eV in the vicinity of valence band H.
Mm-hmm. I guess. Is there a marker here?
On the table.
I don't know what I kind of visualize doing was. Like if that's our hole.
Uh-huh.
Yes. And then at the end of that, showing that after it cools, it forms the polaron.
Uh-huh.
And then we calculate those transitions for our PL quantum yield.
Yes.
Or to try to relate
But
the figure to the table.
if you compute rates for geometry that is already being optimized for the positive polar, when you go from like, okay, we'll talk in person. It's many things.
Yeah. Basically, just one more figure to put here. And then
Yes, please.
move the stuff up.
And you can put green figures of standard dynamics.
Mm-hmm.
Would be cool, even if they don't.
And then, so the main takeaway, or at the end of the day, we calculate radiative rates using Einstein coefficients, non-radiative rates from Redfield tensor. And what we find is that the radiative rates are on the scale of, or no, other way around. So non-radiative is on the scale of inverse femtoseconds, and radiative is on the scale of inverse microseconds. So there's 6 orders different magnitude. So basically the yield is 0.
Can
for
you
these
put,
models.
instead of 0, put like 10 to the minus 6?
Yeah, I can do that.
Because 0 is suspicious.
Mm.
And how would the non-radiative rates change if you drop the temperature to liquid nitrogen? Can you do it without, of course, when ideal, one would rerun all couplings at lower temperature, but can you just scale it down and tell that it will be like linear or according some other function like Bose-Einstein distribution will be smaller rate, and then the quantum yield will change and will become slightly bigger. If it is already 10 to the minus 6, it will never flash
like crazy, but it will be a little more efficient at lower temperatures.
Mm-hmm. If, well, they don't know anything about perovskites anyway.
Huh?
If they don't know anything about perovskites, because I guess the counterexample of that would be if you lower the temperature, you
There will
lower
be
the polaron.
phase transformations. There will be
Yeah.
many things.
Yeah, I can try to put something for that argument.
Did you ever think about transient absorption? If this model doesn't emit efficiently, but when it is already excited and system experiences population jumps from state to state, then there will be additional transitions available for absorption, so time-dependent absorption. And it is one of the available spectroscopic probes that could be already reported in experiment or will be reported soon because it is an inexpensive experiment.
I know it's on whenever we get coupler oscillator strings. Or I guess I could just use the ground state oscillator strings. I don't have.
We use oscillator strings for polarities.
Right, and just do that for the dynamics.
Probably no time for the contrast next time. Let's thank Aaron. Any questions? If no, there is a hope, at least Aaron has hope that there are some written comments to him. And in the remaining half an hour, we plan to complete Fatima, would you like to guide through your poster? So, Daniel, probably you present on Friday. Okay. You see it's not very practical to use this.
Friday.
Yeah, thank you. Yeah, just a second. Daniel wants, or at least he doesn't object to present material based on higher level calculations that we all may practice in years to go. Okay.
Yeah. So we are interested to silicon nanowires because they have some optoelectronic properties such as band gap, radiative, non-radiative transition. And all of them are dependent on momentum dispersion along the growth direction. Here we calculated non-radiative lifetimes of electrons and holes for two silicon nanowires drawn in 001 and 111 reactions. Without with momentum conservation and without momentum conservation. And we tried to calculate photoluminescence. That is, for photoluminescence, momentum is conserved. As you can see here, the band structure of these two silicon nanowires. So if light pulse is applied to the silicon nanowire model, electron can travel from valence band to conduction band. And on the right panel, we can see how photoexcited electrons come back to the band edges. So there are two pathways. For one pathway, electron can come back to the band edge through same K point, and electrons can come back to the different K points. So if electron comes back to through same K point, we call momentum restricted. If electron travels through different K point, we call it momentum unrestricted. There are many pathways here. I just showed a couple of them. Now the methodology. So we used for calculating electron lattice coupling. We used one electron quantum equation, and the solution of this equation is this one. One electron quantum wave function. As we know, upon photoexcitation, electron travels from valence band to conduction band, and they come back to the band edge. When they are coming back, they can couple with the nuclear motion. So, and using this equation, we can calculate the electron, the coupling between electron and nuclear. That is called non-adiabatic couplings. Once we have this non-adiabatic coupling, we can derive autocorrelation function here, and using this autocorrelation function, our rate of transitions can be calculated.
So for autocorrelation function, how many indices are available for coupling? Coupling V, the coupling counts 2 times, right? V, Ij, K prime, and then V, KL, KK prime. Why? And neither one of these 4 indices should coincide generally.
So here, this is time at time t, and this is t plus.
Yes.
For time steps.
For practical calculations, we often make some indices coincide because we are looking on a segment of red field. But if we write down general equation, it should be different indices. Like here, band indices are different, Ij, right?
Oh, okay. So
And here
I
we
need
have
to
KL.
M or something.
No, Ij, KL is okay. M is better just so that it doesn't interfere with letter K, but for band indices are okay. But then for momenta, it's like KK prime, and here should be like double prime and triple prime. And here two indices more, so like 8 indices. It doesn't change things for practical calculations, but in the environment where we will come, some may object.
Okay, so all of them should be different K points.
Yes, yes.
4 K points total.
Yes.
Okay. I understand. And one can derive rate field tensors from the rate of transitions. Here is the time evolution of density matrix, which uses energy dissipation. And the last term is electron energy dissipation term.
See, here you have for red field tensor, it's right amount.
Okay, and then we can calculate the non-equilibrium charge distribution, which is a function of energy and time. Here, this term is the equilibrium charge distribution. And at low temperature, this term is if index I is less than or equal homo than 1. This is the direct delta function. And this is also summation of states. Yeah, so it's IA.
For your low equilibrium, it has all of the indices for bands, but doesn't have indices for K. Should it be also?
This is charge distribution. So
So it's already before summation over K. Just let's discuss or think about if additional indices are needed.
And this is the expectation value of charge carrier. We assume a single exponential function to fit this energy dissipation to get the rate of relaxation of charge carrier. And this is the equation for calculating relaxation rates of charge carriers. Using this equation, we can calculate the photoluminescence, but there is one term missing here, that is oscillator strength. I need to fix it.
Exciton, maybe excited state dynamics. Before this equation for photoluminescence, put excited state. Because in the approach that we practice, there are no excitons.
Oh, exciton.
Our neutrons and holes do not
Okay.
interact.
And here, probably I need to change this name also. So as we know that there are 4 K points here, and for each K point there are 80 orbitals. And in order to calculate further electron dynamics and relaxation rates, we need to combine all of these orbitals in a single file. This table shows how those bands are arranged in that single file, which consists all orbitals for all 4 K points. For here we can see 2 indices. I is for HOMO and J is for LOMO. We consider this is the energy of that particular band. This is momentum variable. I mean now which band it is and at which K point it indicates this column. And these are the initial states. These states, this number we consider when we calculate this electron dynamics, relaxation rates. So in order to calculate electron dynamics and relaxation rates, we consider this initial band number. So HOMO we consider 1 and LOMO we consider 1 for HOMO we consider 1 for hole and LOMO we consider 1 for electron. And these are the numbers. So in that single file, which consists 320 orbitals, 160 is the HOMO. Since we considered 40 states above LOMO and 40 states below HOMO, so we considered from 81 to 120 and 90. 120 is the HOMO. So 40 times 4, 160 is that's the HOMO for that resulting file, which consists all of the orbitals for further calculation. And 161 is LOMO. Then and it continues here. So if we consider calculation of photoluminescence, these 2 states should be same. We can see for this column for silicon 100 and this column for silicon 111. Here we can see these initial states, I would say, they are same. Like it is 65 in that single file, what I described before. So since that is 65, so that's LOMO plus 17 and it is at gamma point, and HOMO minus 17, that is also at gamma point. These are the absorption spectra here. Here I consider different states. That's not the same states. Same initial states for both electron and hole. This is not completely photoluminescence, it's dynamics of excitoners. So we focus on dynamics. Photoexcitation starts at I think 4.6 or something. And this is our time integrated emission spectra, but time resolved emission spectra is missing here. So this calculation is not complete yet, and something needs to be fixed here. This is electron relaxation rates for electrons. And these are these graphs for relaxation rates of holes. There is a difference between these two graphs. Here we considered only 10 states above HOMO, below HOMO, and 10 states above LUMO. But here we considered 10 states based on the highest oscillator strengths. The same thing happens here. This is for 10 states below LUMO and 10 states above. 10 states below HOMO and 10 states above LUMO. And this is 10 states for highest oscillator strengths. And we can see here for a couple of initial excitation, these initial transitions, they follow gap law, and after that they follow inverse gap law here as well. But for them, for holes, we can see they follow the gap law for most of the gap arcs. And this figure is supposed to go here. So these figures just show how electron and hole travel from excited state to the band edge. So this is initial. These are actually snapshots from video clip. So this one is initial state, and this is final. And this is for initial.
Can I interrupt?
Sure.
So, if possible, I know that time is up and it could be not enough time, but the energy. So this function has two components. Y is energy, and x is momentum. For energy as function of time, you show the equation, and you can even make an arrow. But one may want to add another equation for momentum as function of time. It will be like very similar to this one, like this delta n, and instead of energy, put here just momentum.
P.
Yeah. Sorry for interrupting. Please continue.
Yeah, I'm almost done. So here is the conclusion. Conclusion is we considered momentum restricted transition and all transitions which include momentum restricted and unrestricted. So in case of all transitions, our relaxation is quicker compared to momentum restricted transitions because there are additional channels to relax to the band edge for charge carrier. And that's all.
Okay, thank you.
Question?
I'm sorry, could you explain your energy versus momentum graph? Which is the hole, which is the electron,
Here?
and what are those little squiggly lines, the red and the blue, trying to indicate?
So,
I'm sorry, I'm going to ask too many questions. Which one is your hole and which one is your electron?
oh, yeah. This is the valence band, this is conduction band, and these are the bands.
Okay, what is the red line and what does the blue line
It's
represent?
the trajectory of electron. So electron travels this way to band edge and hole travels this way.
Can I make a suggestion?
Sure.
Maybe draw an arrow tip on the show that movement is going this way, and then maybe an arrow tip at the red, just for presentation purposes, because I didn't quite know. I mean, I figured it was a path. I didn't really know it was a trajectory. So, but I mean, I guess it's more or less the same thing. It's the path it's taking. So just a suggestion. I wasn't for sure.
Okay. Thanks. Any
There,
other
there,
question?
there will be people who will look only at this figure. It's because it summarizes all your work and you've discussed about it. With great excitement. More questions? I have one quick one. So do not erase anything, even if you find errors. Right now it's too late. But just think and try to analyze. Here, the energy as function of momentum has maximum, right, in the middle of the band. So it is 111, right? And here, when you introduce the top of the valence band is at gamma point. Like, why the band structures happen to be different in these figures?
Yeah, so this is the problem with silicon 111. For calculating this, all of them, if I consider homo minus minimum state plus 1, then it does not work.
It could be some very easy to fix technical detail related to your table. Maybe making some tricks of swapping order of the elements in this table, how to go from number of band and k point to overall index, we will fix it. I don't know right now. It's hopefully it's easy to fix. If there are no more questions,
I have one last question.
and we have one more talk before the class.
Okay, the one lighter blue, does that mean anything, or is it just an artifact of the graph?
Which one? This?
No. On your far right graph, there's a lighter blue on top of your bottom. I didn't know if that meant anything.
Perfect question.
Here?
It's hard to
Sorry.
And there's like some right.
I believe their electron density.
Yep.
So density, since I am considering these K points,
You said it was electron density?
Whole density, right?
whole density goes electron density.
Cool. Forget it. Thank you.
Charge density.
Charge density.
Oh, for making it maybe more easy to understand for those who come for like half a minute, one can add color bar at a side. And when you do it in MATLAB, there is a button to click it and get it. Okay, let's thank Fatima once again. So hopefully there are some written feedback. No, I'm doing something wrong.
Okay, so in this study, we want to figure out the gravity of diazonium salts on silicon surface. So typically, silicon surface is passivated by hydrogen, and the silicon hydrogen bond is not stable. So at elevated temperature, it can decompose. So to avoid this, we need to replace hydrogen by some ligands. For example, we can replace them by carbon rings. So because carbon silicon bond is quite stable, so at high temperature, there will be no changes at all. So here is my, I guess I have two goals for this project. So the first goal is to figure out how this kind of grafting reaction happen. The second goal is to find out what kind of effect will this functionalization introduce into the silicon surface system. So here is my model. This is a silicon 111 surface. And this is the diazonium molecule. So first I do ab initio molecular dynamics at high temperature at 2000 Kelvin. So this is a graph. This is interatomic distances along the trajectory. So the blue is the carbon-nitrogen bond, and the red is the bromine hydrogen bond, and the green is the carbon-silicon bond. So basically, initially the carbon-nitrogen bond it's like 1.5 angstrom, but as time goes by, we can see the breaking of carbon-nitrogen bond. So for example, at 300 it's like 6 angstrom. That means the nitrogen is away from the carbon ring. Next, we see the formation of hydrogen bromine. This is a hydrogen bromine molecule. And finally, we see the attachment of silicon ring to the carbon ring to the silicon surface. Because we are running ab initio molecular dynamics at high temperature, so we see some reconstruction at the surface. So in the next part, I show the basic electronic structure of a different system. So here, for this system, the surface is passivated by hydrogen, and here we replace one hydrogen by the phenyl ring, and here is half the surface is replaced by the phenyl ring. For here, all surfaces are replaced. So this is the density of states, and this is the absorption spectrum. So basically, we find the top three are very similar, which means the functionalization have minimal effect. But for the final figure, we can clearly see the decrease of the band gap. This is because for the HOMO, the carbon ring introduced a new state. So because the phenyl ring is kind of large, it's kind of bulky, so there is some pipette stacking or some reconstruction of the surface. And here I show the charge carrier dynamics for this system. So for example, this is the charge carrier relaxation as a function of time and energy. This is from HOMO minus 30 to LUMO plus 18. So, and this is a race for the relaxation. And this figure shows kind of the exciton. So basically, what we did is at each time step, we calculate the energy difference between this state and this state. So we kind of follow the evolution of excitation energy. And here I show the time resolved emission. This is the time integrated emission. So I guess the most significant peak is for the intraband transition. Yeah, that's it.
Okay, then thank you. Questions?
So your dynamics was for which model? For what model there?
For this one.
Sorry, you said you didn't see much change in the density states before or after the addition of those ligands, or those groups?
Up to this point. Wait.
Up until this point. What is a half ml?
Monolayer.
Monolayer, okay. So why did you not see a difference up until that point? Did you think hypothesize?
If you see the p-dots, we can see the carbon orbital is like very deep.
It's deep inside,
Yeah.
so it's so like more. You have to have more crowding on the surface to have kind of okay.
Yeah.
What will be the density of states and absorption if one removes any of it, including hydrogens? Is it possible to say that the gap will be closed completely? And did you have like much smaller absorption?
Not necessarily, because for amorphous silicon,
Amorphous silicon with or without hydrogen?
without hydrogen, we also see some band gap, right?
But it is like very small.
Right. But here it's like 0.7 neutron.
And there it is like 0.2. So what, in your opinion, what is most important achievement of this work? The reaction dynamics or optoelectronic properties?
I guess just reaction dynamics.
Okay, so reaction dynamics is more important. Is there any way to quantify this reaction dynamics other than show interatomic distances? Is there a critical temperature, like if you cool it down to liquid nitrogen, would it stop the reaction? Or if it is a spontaneous reaction, would it go at 0 Kelvin without any heat? If one just places the diazonium salt close to the surface and let it optimize, would it do the same reaction?
Not sure about that, but experimentally, this kind of molecule is very reactive. So I know just a little bit of sonication will induce the reaction. So I guess maybe at low temperature, if we run application molecular dynamics, we might see reaction as well. But for long trajectory.
Very small activation energy.
Yeah.
If one repeats this at different temperatures.
Yeah.
Is it exothermal? Are there proofs, numbers telling that upon reaction total energy is small?
I didn't calculate the energy difference.
Yeah, it's probably no time now, but for like if it is more important, then when we add a little numerical quantify. More questions to you? Hopefully there are some comments on the write-up. Questions 1, questions 2, question 3. Well, thank you once again. So please make last changes, interact to each other, interact to me if needed, and plan of submitting to printing like Wednesday night, if possible. And Thursday night is last date. Do not postpone submission to Friday. What else? We may see each other on Friday for another meeting, which will be primarily for Dr. Kivan group. That David will present their something about. I'll announce his work. Multiple spawning approach for excited state dynamics. So some of us were running into literature on this subject, right? Okay, so meeting is done. There will be a class here to continue. And
So will it be in this room on Friday then? Or
no. The scheduled room is QVB 422 on the first floor.
422, at what
But-
time? What time will it be?
3 p.m.
Okay, because we have the seminar at 3:30, so I don't think I can make Friday.
But one of the speakers fears cameras and asks if it is possible to do in a room without camera.
Oh, no.
And it is not David.
Okay.
Dave was not upset about that, though. Of course, this is the first they've heard about this. What's that? I think so. It's Saturday or something. I can't remember. You wondering like when we're flying out or heading? So, okay. The ones we got on the last set. No, they aren't.
I got it. Literally just 3 microscope slides. Yeah.
Thank you so much for your email. It really helps.
Not a problem.
Yeah.
I want to make sure that you do not upset your advisors.
Oh, no.
Some people are really sensitive and they do not want to speak.
Oh, no. And Dr. Kroll knows about all that I'm doing, so he's very just interested in finishing up. He wants to retire.
Yeah, the rules do more. One's right next to it.
Yeah, it was funny because I told Dr. Basil this morning, just talk to Dimitri about the quantum dots because I'm not too familiar. Like, so I was like, okay, sounds good.
If you see anything eatable in the room, please do not hesitate.
Okay. And here is the homework.
So
I tried. I think there might be a sign error somewhere, but I think I got most of it. So,
okay.
I think it happens pretty soon when it goes to 0. Like you don't have to go too far down. This is negative, and then some guys went past 6.
As soon as they continue to get smaller and smaller, it's fine.
Yeah.
So is it supposed to go back and forth?
Can it oscillate?
It will oscillate, but
Okay.
it should go smaller and smaller.
Okay, so mine did oscillate a little. So
You mean closer to 0?
yeah, it'd be closer to 0.
Ugly. That's okay. That's okay.
Delicious.
Forgot to write my name on mine.
So those all your students that work under you?
Huh?
Are those all your students that work under you, or is that a class, or what is right before this?
Some of them will not welcome if you call them students because 2 of them are postdocs. But yes, there are some projects together. But we often do joint group meetings for several groups, just to have like brainstorming.
Never had this happen before.
It's much good. Thank you. So no one did the atomistic models?
I did, but I didn't know.
Huh?
I didn't know what to like.
Oh, just print structures. Thank you.
Nice and simple. Is that not what you wanted?
Flowchart is not.
Not the best chart for it.
It is charged for something else. Okay.
I know it's not the best chart for it.
So, yeah, thank you. No one brought this, yes?
Yeah, we thought only wanted that, the calculations that, I mean, I guess some of us got out of it. Did you want more or everything from that assignment that you sent?
I wanted the structures.
Oops. we got
But
confused.
we can transfer them to the next homework.
Okay, that's fine.
And
I thought it was something we were supposed to do in Gaussian and reproduce that way or something.
no, in Gauss-U, because
Okay.
when we'll get back to, so let me share plans. We need to get through some minimalistic use of Gaussian for electronic structure, and it is boring to do it for the same structure all the time. So I need to see variety how structure depends on how electronic structure depends on like morphology. Therefore, we need a few more models. And the ones that were mentioned in the homework, probably we'll just spend time and do them all together at the beginning of Wednesday, but they are challenging. Some of them do not have explicit bonds, and they may be not right away makeable. So we will on Wednesdays, and we will miss a Wednesday next week. I will be on the conference, but I will connect on Tuesday and Thursday for lecturing online. So please come as scheduled. But there will be no Wednesday lab because it is not possible to do lab through video conferencing. Too challenging. And there will be again distribution of different tasks for presentations. And this will include what we covered last time, like color, the ionization energy, affinity energy, then so-called density of states, orbitals, and maybe some additional quick chapters for Gaussian software. So it looks simple, and we'll try to distribute it over a dozen people. So what are we doing right now? Some of you have connected to preview broadcast last Thursday, so I will be
What we have.
everyone good?
Oh,
In?
oh, cool. Thank you.
Yes.
Thank you.
There are a couple more there. So, in some sense, we are starting the course today. Everything before was also related to the course, but it was, how to say, it was computational chemistry in the broader sense. Starting from now, we are diving into computational chemistry in a narrower sense. And the main thing for grading our practical skills. So we will try to do things easy to digest discuss. But it is completely normal if you feel the material slightly irritating or complicated. So some concepts that we will be going over are, how to say, intellectually challenging. So do not fear, they were and they are intellectually challenging for me, but you need to come over these things. And I didn't took with me the finger writing thing, but if needed, I will be doing things on a blackboard or just verbal addressing. So I'll go over we met for the class about a week ago, so it's better to make a refresher, and it will take substantial time. I'll try to scramble it and go quick, but it's not easy. Just if without explanation, if you just verbalize all things, it will take time. So there will be two things that we need to take out of the classroom. Take home message. Maybe even one. The concept of Slater determinant. So if you have heard about it before, give me a little sign. 1, 2, 3, 4, 5. Okay, if you never heard about Slater determinant. 1, 2, 3, 3. Who heard but not sure? Okay, well, 3. So it's a perfect audience. So most of you were exposed. So I'll give brief introduction because slides may stop us from true interactive communications. We did finish everything, well, not everything, but necessary minimum for nuclear degrees of freedom. We agreed that they are point charges to good level of precision. Now we need to focus on electronic structure. Again, we have a challenge of a really huge number of electrons, right? And I'll show some examples to see how terrifying it is. Arguments that it is not tractable by modern computations. So one needs to stay on the road of ancient Romans, divide and conquer. So we need we divided electronic and nuclear degrees of freedom. Now we need to split electronic degrees of freedom on something simpler. So we need to go from multi-electron wave function, if possible, to one electron wave function. It's not always possible, it's not always correct, but it is only way to survive. And we already discussed about separation of variables, of representing wave function of many variables as product of functions of single variables. Okay. So we did. And we are going to practice similar thing for electrons. But electrons are fermions. They follow what was ordered to them by Pauli, exclusion principle, that you practiced in kindergarten when you were filling atomic orbitals with electrons, right? And due to this exclusion principle, one cannot immediately practice product of one electron wave function into multi-electron wave function. There are some advanced rule which is named Slater determinant. So if you are taking notes, you may try to record this idea by your own words. So take home message from today's meeting will be a rule how to compose multi-electron wave function of single electron wave function. And it will be similar to product, but not product. I hope I intrigued you enough. So if you look on the handout that was distributed, it is related to Jabo and Ostlund book, and it takes a really high-speed interstate highway. We do not need to drive so quick, but if I miss something or you do not trust me, you can browse through and see how they go through this material.
So we're trying to make a more complicated system less complicated. with describing the electron. So going from multi.
I hope I understand you, and I hope you are telling right
Okay.
things. Please repeat.
So we're going from you said a multi-electron system down to a one.
Yes,
Like
from more complicated to less complicated, yes.
And this will describe our system in a way that it's easier to interpret, maybe, or kind of.
The question is easy to interpret, yes, but in addition, there is a more important thing. If we do not if you do not practice things that we are going to do, the problems will be unsolvable at all. So it's not question of comfort, it's question of survival.
Okay.
And if you browse through handout materials, you'll see that, okay, I need to be more organized and give more heads up before. So the goal of the chapter that we are covering, let's go here, is Hartree-Fock theory, right? So it has two names. And the first designer of a theory, the first name, did traditional mathematical physics separation of variables, or product of one electron into multi-electron. And this theory is nice to study, but it fails in describing many phenomena. So the only contribution of, so we will be studying Slater determinant, and contribution of Fock to Hartree-Fock theory is just to bring Slater determinant into here. So he was not designing things. He was just transferred one concept into another concept. And it's enough to memorize his name forever, because it gives qualitatively correct results. Right now, later on, we will use much more correct and practically reasonable theories, but this one is the simplest possible rigorous.
Does this follow force field? Like, would force field kind of be first and then Hartree-Fock?
No.
Okay.
No. It's good that we are speaking freely. We are departing from nuclear degrees of freedom. We will nail down positions of ions and forget about their ability to move for like 2 months.
Okay.
Like, it's a game for kids, freeze. So all ions are frozen and only electrons can do something. Okay. And also, I'm kind of recalling for myself, before we go to the take-home message, there will be a quick recall of the atomic orbitals for hydrogen, which we all are supposed to know, but just in case, it will be a quick recall. So here is John Slater, who did several contributions, and I know why David declined to travel to Sanibel Island this year. He probably got feared to die there. No, there is nothing scary there. You were there.
I was there, yeah.
So it's a quick overview of what we did before. So we did form the atomistic model when we quantify. Thanks so much. When we quantify positions of nucleus and electrons, and then they are used to form the Hamiltonian, and then as a major outcome of our chapter 1, that we were able to separate nuclear and electronic degrees of freedom. So for electronic degrees of freedom, we have 3 terms in Hamiltonian: electronic kinetic energy, electron repulsion, and attraction of electrons to nucleus. And for nuclear degrees of freedom, we formed Schrödinger equation. We went from time independent to time dependent, we made classical path approximation or point charge approximation, right? Instead of expectation, instead of nuclear wave function, we went to expectation value of nuclei, and then we derived equation of motion for these average positions. And in your homework, you were optimizing them for oversimplified model, right? So from now on, we have basic idea how to optimize geometries and what are, they have equations that rule positions of ions do keep some contribution from nuclear degrees of freedom. So this energy includes, I do not see this equation here, but it includes nuclear repulsion and eigenenergy from electronic degree of freedom, right? We went through it before. So for the sake, even if we are looking only to optimize geometries, right, we still need to solve for electronic states. And before we were assuming that solutions are provided by someone. Now we need to look how to develop them. So our Hamiltonian becomes simpler, only 3 terms, right? All ions are just point charges. So our goal for next, whatever, a little less than a month is to find these wave functions and these eigenenergies, right? And previous homework, you were bringing images like this. Okay. So it's homework. So we are going to keep kinetic energy of electrons, energy of electrons interacting to each other, and energy of electrons interacting to nuclei. And before, if there would be no molecules in the universe, this class will be cancelled, right? Because if there are no molecules, then there are no chemistry and there is no computational chemistry. So some physics classes will be still allowed for atoms, electrons. But before we go to molecules, when several atoms are collected together and have shared electrons, we may look onto single atoms and just quickly overview the eigenstates of electron in the hydrogen atom or hydrogen-like atom which has bigger charge. Why we need it? We don't need it. It's easy to assume that you all know it, but we better declare it quickly so that we speak on the same language, right? So before going to hydrogen, I promised a quick scary story. So why computing electronic structure is so scary? Why it is scary for programmers and for computers and for humans? So let's practice the same game as we did before. Assume that we do not know and we do not like math. That we maybe some of you have hidden love to math, but we will hide it. So our goal is solve everything numerically, which means discretize any independent variable and compute values of any function at any discrete values. So just for easy estimate, let's assume that any Cartesian coordinate, Cartesian projection for position of electron is discretized over 10 grid points, just because of 10 fingers. And because we have a decimal calculational system. Then for hydrogen atom, how many independent points we need to represent wave function of hydrogen. If for 1 degree of freedom, you have 10 points. For 1 degree of freedom, 10. For 2 degree of freedom, it will be 10 by 10, 100. For 3 degree of freedom, it will be 1,000, right? So if we need to solve for hydrogen atom, we can just split space around nuclei on grid points, write Schrödinger equation in numerical form for each point, solve them, and represent as such cube files, right? It is possible. We can record them in Excel, we can analyze, we can do anything. No problems. If it will be either helium atom or H2 molecule, there will be 2 electrons. And if you split space on 10 grid points, and we have 3 times 2, so 2 electrons, 3 Cartesian projections for each of them. So 6 degrees of freedom. It will be million points, right? So if we go to atomic carbon, not a molecule, just single carbon. So what did we learn in the kindergarten? 1s2, 2s2, and 2p2. 6 electrons, 3 Cartesian projections for each of them. 3 times 6, 18. So 10 to the power 18. It's amount of grid points that we need to set up equations to solve just for carbon atom, electronic structure of carbon atom. And terabyte, how much is it? 10 to the power, how many bytes? 12? 10 to the 12? That's right? So 10 to the 18 will be just a million terabyte. Like a terabyte is what you can go into store and buy a drive. So you buy a million drives and you're able to describe carbon atom. Right? Nice. And then if you just need a pathetic acetylene, I even do not want to pronounce, 10 to the power 42. So it will be too much hard drives just to store the wave function. So the goal of this slide is to scare you. I'm feared of. So it's a literal recording and solution of multi-electron wave function is a little expensive for us today. Especially if you want to go behind 4 atom molecules. Right?
Basically, the point is to show us that computers don't have enough computational power to solve the Schrödinger equation for a huge number of electrons. Okay.
Yes, yes. So, but we are so brave that we just will design tricks to avoid this barrier. So what we understand under this phi sub a is function that depends on position of each of ions and each of, not ions, electrons. And each vector means 3 Cartesian projections, is what we just call. So what do we do when we have function of too many variables? Separate variables. We want to represent this function as product of some simpler functions of each of these variables, if possible. Right? And we are going to practice this idea and get some moderate success. We just need to do it carefully. Whatever we will be doing will be not rigorously correct. We will not get absolutely correct answer. It will have some level of precision because electrons interact to each other and they are not independent. So even with all care, the representing multi-electron function as product of one electron function, even with tricks, even with later determinant, is not an absolutely correct thing. But there is nothing else to do. So when I was offering this course for the first time, I went to a conference and a postdoc from my group was giving this lecture, and he did nice slides, so I'm still using them. So our Hamiltonian does have three terms: kinetic energy of electrons, attraction of electrons to nuclei, and interaction repulsion of electrons. If it is hydrogen atom, which term do we drop? First, second, or third?
Third.
Correct. Thank you, Kevin. Why? Because there is only one electron. It doesn't interact with other electrons. If it does, then it is self-interaction error. Okay, so we drop third term. We have only two terms, and it is one of the few problems in the world that can be solved mathematically correct, absolutely precise. Again, we are not in the math class, so we don't care about solving it. There are some classes that solve it, but rigorous, careful solution, it takes at least a month. If one doesn't skip steps. But the solution is possible. And at least every one of you is aware with this notation, right? So wave function has how many quantum numbers? There is a little lie here. 3, right? 4. Principal, orbital, magnetic. Magnetic is favorite quantum number of gauge, right? And spin. So let me see if it can. No. I do not like these figures and this discussion, but we need to do it once. So if you measure distance of electron from the center of hydrogen atom, there are eigenstates, right? And they differ by quantum number, principal quantum numbers, right? Another thing that so it determines the energy. Then in addition, the electron may rotate with different pace, having different angular momentum. This second quantum number, orbital. And then for the total amount of kinetic energy associated with rotation with angular momentum, it may be oriented differently in space, have different projections on specific axes. This will be a magnetic quantum number, right? So, and the mathematical solution for this is obtained as product of two functions, one of which depend only on distance from center, and another is function of angles, right? Why two angles? Because, yeah, it's nature of Hooke's theory. And each of these functions are mathematically rigorous. They can be expressed analytically, at least through series. So there are spherical harmonics for angular dependence and Laguerre polynomials for the radial part. And most interesting part, this polynomial is hidden, but it is known. And when we draw orbitals for hydrogen atom, we basically practice this function. So intuitively, all of us know how they should look like. Right? A little comment that is always, not always, but often skipped in the when people try to draw atomic wave functions. The solutions for spherical harmonics do have the imaginary. The dependence on magnetic quantum number accumulates phase as one goes along this azimuthal angle, right? But humans like figures without imaginary numbers. So what is done all the times and hidden from attention of students is that one takes solutions with opposite values of m and then add or subtract them. So when we draw p or d orbitals, it is the result of this procedure. When you add or subtract, well, when you subtract, you need to divide by imaginary unit. But the wave functions that one draws, they are real, right? So there is a procedure how to convert two imaginary functions into two real functions. Who we are and what are we doing? We want to describe multi-electronic wave functions for any molecule. Our goal for today's meeting and take-home message will be Slater determinant, which is a procedure how to construct multi-electronic wave function out of single electron wave functions. And on the way to this Slater determinant, we are going through a quick recall of the atomic wave functions, because they will be building blocks to form molecular orbitals. Well, molecular orbitals not today. Multi-electron wave functions.
So anytime you see one has a negative I in there, you're gonna do the opposite. You're gonna make it easier to add.
If you need to draw it.
If you need to.
If you need to do some mathematical operations, imaginary unit and functions of imaginary unit are really comfortable.
Okay.
Because they're easiest thing to integrate or differentiate.
Okay.
So, who never saw these images? Who is very comfortable and can explain what they are? Okay. So about cup, happy to explain. So what are they?
Molecular orbitals.
Huh?
The molecular orbitals.
Which orbitals? Is it right?
Atomic.
Atomic orbitals.
Thank you.
Okay.
Atomic orbitals.
So what are the axes? So orbital quantum number and magnetic quantum number. So we are neglecting dependence on the offset from the center, just looking on the dependence on angle, right? And the states with small principal quantum number do not have comfort to practice different other quantum numbers. For lowest state, you have only one. But as far as you go up to larger and larger principal quantum number, you cover more and more these exotic shapes, right? So it is what you saw as S, P, D orbitals, right? One first shell has only S orbitals. Second shell has 2s, 2p. So this indices 0, 1, 2, 3 correspond to SPD, right? And the magnetic quantum number corresponds to which part of kinetic energy of rotation corresponds to rotation along z-axis, right? So if all kinetic energy of rotation is represented by rotation around z-axis, so it will be around z-axis, then fringes, positive and negative, will go across this path. If there is zero projection, if there is no component of kinetic energy associated with rotation in the xy plane, there are no nodal points, nodal planes as we go across. All the minima and maxima will go only as we change angle theta, right? From top to the bottom. What else? who did hear and practice the word isosurface?
Say it again.
Isosurface.
Isosurface.
1, 1.5, 1 2/2. Who never heard the word isosurface? Majority. Okay, so the atomic orbitals are three-dimensional functions. They're defined in each point of space. But it is quite complicated for humans to visualize it, right? One needs like to have a fog, clouds, right? And instead, there is a way to represent three-dimensional objects by selecting surface of the equal value of a function. So it is a surface where we have probability density or amplitude of probability density, let's say 1%. And then it will form these shapes. It means inside these shapes, it will be higher density, outside sparser density. But these balloons are a little easier to represent compared to three-dimensional shapes. Make sense? And we did miss dependence on the offset from the center. So for the simplest one is orbital. We again, this if you are tired, lean back and relax. I will let you know when to wake up and when there will be most important message, and it will be about later determinant. Now we have just a little decoration.
So the sorry,
yes, please.
So the isosurface is the probability of where the density would be. It's more kind of like a cloud, not so much more a discrete kind of low, what we see at the atomic orbitals.
We will go through this concept several times. So if you have one-dimensional function, and we set up a threshold value, so we pick up only values of a function where function equals this, let's say f0. So it will be points, right? Now, if we do have two-dimensional function, x1, x2, right? So it's complicated.
So it's kind of like a contour map, kind of.
Contour map is a surface in 2 dimensions.
Okay.
1D, 2D. Then we set up f0 value. We draw a plane. Do we have another color? Okay, I'll try to be artistic.
Oh, I see.
So a line where function is equal to predetermined value will be isocontour. So here may be iso point, here will be isocontour. And if it is a three-dimensional shape, which is really hard to draw, we can also select such object in space where function equals to predetermined constant value.
Right, and it's a slice, so you can slice it.
Slice from
different
slice.
to get.
See, we go from 1 dimension to point, which is 0 dimension, reduced dimension. Here we go to 2 dimensions to line, which is 1 dimension. In 3 dimension, we go to 3 to 2. So we go from 3-dimensional distribution to 2-dimensional surface. And isosurface is just from 3D to 2D.
Okay.
Okay. Where we are? So wave functions, psi, n, m, l, and we skip spin for now. Product of radial and spherical. Theta, theta, right? So we already discussed the spherical part, and now quickly focus on the radial part. So it is how the radial part of wave function depends on position. For the lowest state, for the 1s orbital, it has maximum right at the atom, and then as we depart from center of the ion, the wave function departs, right? If we are going to (2s) orbital, so next principal quantum number, and we have dependence on the position, which also has maximum in the center, but then it has one minimum and then another thing. Right? If we go to, so here this function has two indices. One is principal quantum number, and another is angular orbital quantum number. So for the p orbitals, it has 0 probability at center, and then some non-zero value in between. Right? Make sense? So this p orbitals have like petals with nothing in the center.
So orbitals are basically probability clouds?
Amplitude of probability. So orbitals are such objects by taking absolute value square of which we get probability. Okay?
Okay, so
square root of probability, but do not, I should take microphone off. Do not repeat it, it's only for development concepts.
Okay.
So orbital is square root of probability, but never say it in public.
All right.
Okay. By the way, if you are, you still have time, if you are tired, and I can make a little break in the presentation and go online and suggest you a nice website that everyone, I promise, will entertain. Did you ever looked at p-table? We did. P-table. So if you select orbitals and you click on hydrogen, and then you look for, since it is one electron, it is in the lowest state. But here, as we go higher up, it will be different principal quantum number, and it will be different values of orbital quantum number, and these cells will be different projections of the magnetic quantum number. So just by browsing through different cells in this table, you'll see shapes of orbitals. It's not isosurface. They try to show three dimensions. So lowest state has quantum numbers 1, 0, 0, and then if we still have 0 angular momentum, it has like one sphere inside another sphere. But if you go to p orbital, it is your favorite, how to say, gym exercise too. Just oriented in different directions. And if you go to next, there will be opportunities not only. You see, these p orbitals have some structure as you go between center and outside. So there's additional fringes because of the radial part of the wave function.
So this means the probability is smaller in the center than it is in the outer parts?
Yes.
Okay.
Yes. And then there are d orbitals that some of you may like.
And are we assuming that all electrons are constantly moving through all of these, or is it just like 2 are only in that zone?
Great question, which is really challenging. So on one hand, we believe in stationary Schrödinger equation. So if you place electron into orbital with certain quantum numbers, it will stay there forever. On the other hand, there is a time-dependent Schrödinger equation. That as time passes by, there is accumulation of mass. even if distribution stays the same, there is a dynamic. Maybe it is not reflected in any observables, but there is a constant accumulation of phase.
Constant accumulation.
Accumulation of phase is multiplying by e to the power imaginary unit times energy times time. So if you take absolute value square, it will give you constant. It will not change anything. But there is a dynamic. So electrons move, we just do not see. Okay? And interactions, yes, they repel each other, and they, on the lowest order of description, they kind of coexist in different orbitals. But as soon as we bring in more and more electrons, they start to repel each other, start screening each other, and there are additional effects. If you were asking about this. Yes?
Okay, I sort of have a, I don't know, a silly or elementary kind of question. Where we have unpaired states, is it going to matter in terms of, I feel like I kind of know the answer to this question. Unpaired electrons, some are so important versus others, depending on which shell they reside in. Because that's going to make a difference in the energy with interaction moving them around.
Electrons like to be paired.
They like to be paired.
If they are unpaired, there are additional energy penalty. If it is transition metals or lanthanides, there are additional rules of filling shells. So, in some circumstances, they like for the high orbital momentum orbitals, they like to be unpaired first. And if you enforce them to be paired when they do not like it, there will be another energy penalty.
Got it.
And this Aufbau, you all have heard the Aufbau word, right? Which means like built on in German. So it's like how this cells are filled with electrons. And if you practice this website, you'll see these illustrations from the orbitals, right? Okay, enough for relaxation. Let's go back into the class material. And I do have a sign that voice is not recorded, but at least the images will be recorded. So, who we are and what are we doing? Our goal is later determinant, to build multi-electron wave function as something like a product of atomic orbitals. Atomic orbitals are our building blocks, right? And we will want to bring together several atoms, form molecule, and then tell that electronic state of the overall molecule will be built of products of atomic orbitals as much as it is possible.
So each atom has its own atomic orbital?
And each of them, most of atoms have more than one electron.
Okay.
So some of them are occupied, right?
Also, each electron in each atom has its own orbital, and they combine to form molecular orbitals?
Yes.
Okay.
Well, molecular orbital is an approximate concept. The more rigorous is multi-electron wave function. Okay. Who can tell about antisymmetry? Who took undergraduate PChem2 for statistics? 1, 2, 3, 4. So, what is antisymmetry?
Isn't it like the literal opposite of symmetry, where symmetry is it's the same reflected, but
Isn't this something with point groups?
Okay, nothing wrong. Everything correct. Let me be more specific. What is antisymmetry of electronic wave functions? And how it is related with Pauli exclusion principle?
chiral? Isn't it when you switch electrons, you have to introduce a negative sign?
Perfect. I cannot write by finger, but Ben 1+. Good. So, before we start building multi-electron wave function, we should make sure that they follow this rule of antisymmetry. And if you glance through this handout, you'll see things about it. So when we swap order of electrons, like probability distribution shouldn't change, but the sign of the wave function must change. Why? This is a really terrible and how to say counterintuitive question. Do you know if you have the answer, some of you may explain it better.
What's the question?
Why swap of the order of electrons in the wave function must change the sign of the wave function?
Well, I guess the wave function seems to be going up and down, so you're changing above a zero mark, below a zero mark.
That's just angular momentum.
No. I like what Midi is telling.
Does that make sense?
It does, and I will try to show it. Maybe it's time to write a couple of equations. It's really a counterintuitive part, and I will try to cover part of this is covered in slides, but first I may draw. So we need a property that if we swap the order of electrons, then the sign of a function will change. This is not a frivolous wish. It is not because I have a mood to change signs of wave function. It is literally dictated from Pauli exclusion principle, which is that two electrons cannot reside in the same quantum state, right? So I'll show a couple of slides, and we may come to the proof of this statement. And this is a true challenge.
Does this have to do with state functions, or no?
No.
Okay.
It is used later for many things.
Gotcha.
So it is what we want. It is not a proof. So we do want change of the sign of wave function and keep the probability distribution wave function squared upon the swap of the order of orbitals. So can we try to compose, to do a little mathematical experiment? Suppose that we already have orbitals, phi1, phi2, and we do want to compose our many electron orbital as a product of such orbitals. So let's just make an experiment. Phi1, phi2 in positions R1, R2. Minus phi1 R2, phi2 R1. So in these terms, we introduce two terms, and you see that here the indices coincide. So in the quantum state number 1, there is electron number 1. In quantum state number 2, there is electron number 2. And here in quantum state number 1, there is electron number 2. And in quantum state number 2, there is electron number 1. So we swap the order. Let's inspect what happens if we swap the order of electrons. So it's not a proof, it's a mathematical experiment. It means I cut and paste. I swap order of electrons here and swap order of electrons there and see what happens. Let's just try it. So phi of R2, R1, and here let's follow this rule. So phi 1 of R2, phi 2 of R1. No errors, right? I just practiced this rule. Now here minus phi 1 R1, phi 2 R2, right? And now let's look how this original term corresponds to first term in the first line corresponds to the second term in the second line. Do you see any difference or similarity? Huh? They're the same with, but there is a minus sign. Now let's circle this one and this one. Second term in first line and first term in second line. Are there similarities? They're the same, but they have different sign. So now we can write down that phi R1, R2 equals minus phi capital R2, R1. Right?
Also, that's anti-symmetry?
Yes, okay. Anti-symmetry of wave function. And if you really want to be picky, we can put brackets and put square 1 over square root of 2 for later normalization. Now, there is one trick that I fear to do and declare and to do. What if we will be so brave to not obey Pauli, to violate his rule? How can we do it with this writing? So here I'm trying to violate Pauli, not Pauli, Pauli's rule. I still have 2 electrons, first and second, but I will try to squeeze them into the same state. So this will be wrong, R1, R2. Now I will practice the same style of wave function. 1 square root of 2, phi 1 of R1, and then not phi 2 but phi 1 again, phi 1 of R2, right? I'm placing both electrons into the same quantum number, minus, and then I'm swapping phi 1 of R2, phi 1 of R1. One. Same wave function, but 2 different electrons. What will be the answer? Huh? Yeah. Everyone agrees? Right? So it's the same function. Phi 1 R1, phi 1 R1, phi 1 R2, phi 1 R2. It will be 0. And wave function must be normalized. It must be non-zero, just by definition. It may integral of wave function should be number bigger than 1, bigger than 0. What does it mean if you get some wrong answer? It's not from this story, not from this movie. Something is wrong. It's not allowed here. So if we accept this rule, which later we will call Slater determinant, we will automatically see that this rule will prevent us from violating Pauli's principle, right? So if by some occasion our solutions will mandate us to violate Pauli principle, it's no such solution. So it's how to say, additional measure against violation of Pauli principle. So if we assume this form of wave function. And I think in previous year it was much quicker. If replacing index 2 by index 1 here and index 2 by index 1 here when it's getting 0. So I can deliver it much quicker than rewriting stuff. I was hearing this part of the presentation. The rest is a little easier. So we're not going to speak about third, fourth, and fifth electron just because I'm lazy. We can get through basic principles only with two. So we declare this functional form, which in some sense it is a product of functions of one argument, one electron wave functions. But it is not product, but superposition of products with swapped order, right? And we just agreed through this little, I wouldn't say it is proof, but demonstration, mathematical experiment, that this is a really good idea, good choice. So we are going to seek for solution of multi-electron wave function in this functional form. And in few minutes, we are going to update it for a larger number of electrons, hopefully. Okay? Declared. Okay. Slater. Why determinant? Any ideas? Slater is the name of a person. You saw that the photograph. But determinant, I'm not lucky to know the person with first or last name determinant. Hi, I'm determinant.
Okay, well, I guess I learned this in like quantum one when you're writing like wave functions. You can represent them in major Z's. I mean you can represent the Hamiltonian in like a matrix, like a 2x2 or a 3x3 matrix, and then when you apply that to like a wave function, you'll get an energy times that same wave function. Now in linear algebra, when you're trying to find like eigenfunctions and like eigenvectors, you like take the determinant of that matrix, set in like equal to 0, and then that's how you find the energy eigenvalues and eigen.
This is not wrong.
Okay.
But what Kevin told to us deals with one electron quantum mechanics. Okay. So all textbooks and like 80% of basic quantum theory or PChem that some of attendees of this class were taking before deal with one electron problems. And what you are telling, there are some basic states, and there is some perturbation. One tries to diagonalize Hamiltonian. And diagonalization includes procedure of finding determinant. This is correct. This is good, but it is not. It's a little different story.
All right.
Now we bring in more than one electron. Yes.
Well, to find a determinant, you take a matrix and you multiply certain elements together and subtract those results from each other. So that's pretty much exactly what you're doing right there. So it's a good way of representing multi-symmetric wave function.
I cannot do it, but everyone agreed. Everyone heard what Nathan told.
Have you found a determinant before?
Yeah.
Okay. So if you have, like, in the top row of a matrix, if you have like f of R1 and f of R1 and g of R2, and then on the bottom row you have g of R1. I might be mixing it up.
So
Or are you gonna mix up the cheese and the house? Different.
Well, so if you have like a 2x2 matrix to find the determinant, you take this one times this one minus this one times this one. So
what is the determinant of the 2x2 matrix?
It's like a AD minus BC or something like that.
AD minus BC, diagonal minus off diagonal, right?
So if you make those functions match up with the A and D and B and C, right? What you wrote there is the same as that.
Like if you see combination of A, D, B, C in this order, you can, why should I memorize the order? Can we logically go from this line to determinant of some matrix? So if we do see combination of phi 1 of R1 times phi 2 R2 minus phi 2 R1 phi 1 R2, can we make connection? This will be our A, this will be our D, this will be our B, this will be our C. Right? And just let's distribute this one electron functions in the matrix that we just designed for comfort. I know many of you develop irritated feelings, like any word about matrix cannot make me comfortable. But it is much easier than, much simpler and more comfortable than anything else. Of course, it's better to just sit on a couch with a beer than thinking of matrix. But rather than writing long lines that are hard to memorize, it's easier to put them into this form. So phi 1 R1, phi 2 R2 on the diagonal, phi 2 R1, phi 1 R2 on the off diagonal. And if you take determinant, we will get exactly this expression, right? So Slater took into account antisymmetry, and determinant took into account a comfortable way to represent it. Make sense? It's already here. And if one assumes that each of the phi 1 and phi 2 wave functions are normalized, and one will practice double integral over R1 and R2 of the many electron wave function, one can get that it will be also 1.
Since we're only dealing with 2 electrons, we're not going to have anything better there too. Bigger than a 2 by 2 in this case.
This is a great homework. Probably not for now, but like next year. Oh, okay. I didn't want to believe that everything what I'm offering is correct. Some people like abstract thinking. Some people prefer very, very practical things. So I have, this one. So what if our function phi 1 will be sine? Oh, by the way, y sine and y sine functions. Let me click something here. Please lift hands if those who took some basic level of quantum theory.
Being quantum mechanics 1 and 2.
Yeah. And who never took any quantum? Who never took? If you never took quantum. Okay. So if you are in this class and you didn't take quantum, you are really brave. But if you perform well, it means that you have supported support for this to be brave. So in the basic quantum theory, there are some favorite problems that everyone solves for with a practice, and one of the favorite practical problems is so-called particle in the box, right? So right now, who are my primary target? Kurt, Queenie, Anas, who are lifting hands, right? So if one has very artificial, it's much simpler than any atom or any molecule, just potential V that is infinite before the box, if x is smaller than 0, and infinite if x is bigger than some number, and 0 in between, there are very standard, well reproducible solutions of Schrödinger equation for such model mathematical problem. And they will have shape of sine. And if you offset them by energy, it will be sine with one harmonic, second harmonic, third harmonic, and so on, right? So the sine functions for the particle in the box are good examples of basic quantum theory, right? Now, what if our multi-electron wave function is attempt to put two electrons into particle into the box? By Pauli exclusion principle, you cannot put two electrons into the first state, right? It should be one electron, R1, in state 1, here, and second electron, number 2, into the state phi 2, right? But since we believe in Slater, and since we believe in determinant, the wave function of two electrons should be composed as we already discussed. But here we can put literally. So phi 1 of R1 will be sine of R1, and phi 2 of R2 will be sine 2 R2. Right? If you go higher up in harmonics, here is sine x, here is sine 2x, here is sine 3x. So quantum number just pops up, making it oscillate more frequently. Right?
So they're only signs then?
Huh?
They're only sign though.
Yes, yes. Well, there is some normalization factor, but we will die if we will and spend waste time.
Okay.
Make sense? Now, let's practice this product. So harmonic number 1, and not as long. So function phi 1 is sine of argument. First electron in the first harmonic. Second electron, x2, in the second harmonic. Now, since it is function of two variables, we draw along, I swap them. Along one dimension, it will be one hump. Along another direction, it will be two humps. So two-dimensional function, plus and minus. Make sense? If we swap order of the arguments here, second electron in first orbital and first electron in second orbital, then it will be same shape, but it will be rotated by 90 degrees, right? And if we subtract them from each other, it will be like plus minus plus will be 0. Here is the bar telling where is positive, where is negative. So first quadrant, plus minus plus will be 0, green color. Here minus, subtract minus will be again 0. Again, 0 line in the center. Here plus, subtract minus will be big plus. Minus, subtract plus will be big minus. Right? So it is example how two-electron wave function looks like. Right? So it is neither this nor this. It is something more complicated. And if we swap the order of electrons in both of them, this plus and minus areas will swap the order as we require, right? So it is nothing new. It is what we already discussed. It's just a little illustration. Make sense? Good. And if you love MATLAB, here are the just little command lines how to make this images. Yes?
So really the vantage point of this is that you'll show kind of sort of a hybrid where things are the further up you go in your, because this looks like to me you're swapping things, but you're also kind of showing a mixture in the last picture there.
Mm-hmm.
So it almost seems like you're covering more area, or you're trying to average things out a little bit nicer. Maybe thinking of that?
I really do not know how to bring it into common sense, intuitive interpretation. I'm trying to develop some words, but I'm trying not to declare them in public.
Really, this is just...
In some sense, it is a rotation of axis of system of coordinates. Before we have x1 and x2, and we always represent it as a product. And here, independent axis becomes x1 plus x2 and x1 minus x2. So we can kind of make rotation in this space.
Okay.
Okay. What else? Yes, it is just if you swap sign, I did check that it changes. Okay. Maybe it's enough for today. Right? Let me tell a couple of words more. So if we have more than 2 electrons, we just practice concept of determinant. We list the orbitals, first, second, third, and along, let's say, rows. And along columns, we will list number of electrons. First electron, second electron, third electron, and then practice determinant. And it will give antisymmetric wave function that will obey Pauli exclusion principle.
So you can have a bigger than a 2x2, and you have 3
by 3 or million by million or whatever. Okay. How many electrons?
Just to make sure. Okay. Yeah.
Yep. So again, what is the benefit? Why we need it? We do not want to argue with Pauli, right? And if you want to, on one hand, on another hand, we need to solve for multi-electron wave function, and on the third hand, we do not have power to do it at once. We need to divide, separate variables. So separation of variables for multi-electron function, just by nature of this problem, is possible only through this antisymmetric shape, which is called Slater determinant. So, and meanwhile, we got some entertainment about hydrogen-like orbitals. So, hydrogen-like orbitals are our building blocks, and Slater determinant is our blueprint. We will fill Slater determinant with atomic orbitals and get, hopefully, wave function. Maybe I did lie a little in the last sentence, but we will see on the next meeting. Any questions about the content? No?
Question.
Yes, please.
So prior to this, we talked about freezing the ions, and we're focusing on the electrons. Are we going to bring that back together?
Yes, absolutely.
Okay.
At the very last 3 weeks of the class.
Okay. So now we're just focusing on certain chunks, and this is the Slater chunk is what we're focusing on.
Let me go to the this navigation map. So the 4 chapters. First one about nuclear dynamics, second and third about electronic structure. And after we finish the 3rd chapter, we all will start intensively digging into research projects.
Right.
So there will be a little discrepancy. The class material will be about excited states and optical properties, And substantial part of the research projects will be about simultaneous evolution of electronic and nuclear degrees of freedom. We will not need additional material in class because it will be already covered in previous chapters.
Excellent. Perfect.
Enough. Thank you much for your patience and participation in the discussion. Looking forward to see you same room, 5 p.m. tomorrow.
Yeah.
Thank you.
I had one like on the another homework that we for extra points. So how you wanted us to solve that? I just like
build atomic models.
Yeah.
In those yes, and I was expecting to like print how it looks like.
How to
print build atomic model, optimize and print. Measure interatomic. Yes.
Downloaded it online and I just gave it for relaxation. So I
it's fine.
didn't
It's
understand
fine.
the questions.
Okay, I'll be more specific next time.
No problem. Like I just felt that maybe you are expecting downstate energy. That's why.
Well, I'm going to ask it in the next round, but I wanted to split building and optimizing from characterization.
You wanted us to draw that stuff.
Yes.
Sorry, so I didn't.
That's okay. That's okay.
You for the model kids?
Yes, let's walk.
Oh, yeah.
Let's walk together. We will walk to Dr. Kilina's office first. She has some kits to share that she doesn't need, and if it will be insufficient, we'll go to my office. I have a few more kits that I need back sooner. But
So kits, yeah. So
kits. KITS.
So we need to know carbon and hydrogen. Sorry, go ahead.
yeah, I guess I don't. Are they all the same? Whatever. He'll show us, and
Yeah.
I'm sure
we
we'll
want
be
to be
good.
able to make a long haul. That's the goal.
Are you in a rush?
Me? They're gone, aren't they? They're so good. Yeah, so I'll have you take care of that. Thank you.
Yeah.
We're doing a thing on Thursday, so it's for the kids.
And you kept saying kids. I'm like, kids?
Kids,
kids.
yeah, not mom.
Kids for the kids.
For kids. Thanks. Have a great night.
You too. Thanks much for.
Yeah, you're welcome.
Okay, so we're good to go?
Yeah.
Okay. So
I need to go work. I need to do stuff. Because if we present it in February, right?
Yeah. Is it end of February?
Yeah, well, the summit or something.
It's after.
There's something in February we present. And then it's like one thing in March.
Damn, I don't know. At this point, I don't know anymore. Dr. Rezzo said, oh, it's empty. I should ask you, thank you. If you knew how, I mean, he just forgot the function, but how to convert directly. Okay, so if I have like an output file from my Gaussian, and I want to convert directly like the last Cartesian coordinates it gave to me to another like mol file or something. He said I can directly use Gaussian to I can use OpenBabel functionality on CCAS to do that.
Yes.
So I was wondering how would you go about
Wait. We didn't have time to go through, but it was kind of my expectation that you'll present to everyone how to use command line Babel.
Oh, command. Well, I'm not.
It's time for you to learn at least for yourself.
Yeah.
I was partially showing it in the lab here.
Yeah.
And we can quickly go over it,
but this one is more about like getting like the. So I'm trying to extract the last coordinate I was given on this big output file, right? So I was wondering, will it just naturally go into the last like my output file and just extract the last coordinate without any like program or anything like function?
Well, try to use Babel. Like Babel minus I, Gaussian 09, space, name of your output, space, minus output, XYZ.
So minus I is the function. So give me a second.
It was in the record. I think it was in the recording of the lab.
Yeah, there was something else missing. That's why I was confused. So I have. This is what we tried. Babel space minus I. Should there be a space in between anything?
No space. But it will not. I'm not sure if it instead of Gaussian job file, put XYZ here.
So I should put
output
output XYZ. Okay.
And I will send. If it will not work, I have another suggestion.
Okay.
I'll bring it to. I'll try to bring it to the lab.
I tried without. I tried this one, it didn't work, so I'll try the XYZ.
It's not Babel who is guilty, it's Gaussian who is guilty.
It's Gaussian?
They forbid people to overuse their format. They have some legal protections.
Okay. Alright, well, I will try it out and I'll let you know tomorrow.
Okay.
Thank you.
Oh, my pleasure. Very soon, I'm almost done.
Where is, how's Kisser? I don't only used it for like a little bit, but there's no hiccups.
How about your payment?
Oh, terrible. 0.399.
Any increase in mixing?
I did everything. Well, everything increased, but everything was solid. Drivable and like the lead and the last quote. I did 5,000.
Level of rotation.
Yeah, I went to like 35, 40%.
That's still low. Go to 60, 65. You'll get the data from that. So he just, like what, they just thought of it, just, do this, do that. Well, what he expects is for us to play around with it, see what can possibly come out of it.
Yeah, I don't understand that, because like Anasa's been working on it for like a month, and it's like, I mean, is there a point where you're just beating a dead horse? Is it saying where it's like...
They're just trying to get a better data.
Yeah.
First of all,
maybe because he is close, right? Because he's close, maybe that's why Russell wants you to keep pushing it.
Yeah.
At the same time, you can't force something that's not there.
But what Manas has right now is better than what they had.
Sure he does. Oh, I thought that was like even or a little less.
It's a little better than what they had the first time because he added a little bit more relationship in there.
So if it was like 75 and us has what, 18?
Probably. The thing was that when Anas did it, even adding Homolumo, it didn't show up on like one of the descriptors that yeah. But then he added it and it made a significant difference to like his results. So how you add that, it doesn't show up, but then so this is something else. So, and then I'm sure he's asking him to add some other stuff too.
Yeah.
Some of the Qsering and S has gone for it. Presentation.
That's what I recall. Now, where's the smallest state? New York, New Jersey. Why can't I pick that state right there? Rhode Island. Oh my gosh. Look back there. At least we need I need to know, I mean, I need to know all the states.
Who competes?
I don't, I can't.
You can share. Okay.
That's Nebraska. What is that? Why is that one down? That one's Nebraska. I can't believe it's there. I thought. Are we, oh, we're ready to say?
Oh.
Catch it.
See you later.
Oh, I see why the sound went off. It's just the battery was done in the microphone.
So the sound of the leg.
So it will be like cinema.
Your call will be disconnected.